Thank you. And he was just trying to post probably the same time you were.
Okay.
Colombia as well. Yeah, the kind of thing. He is kind of different.
I see.
But I think for some reason in the
Okay.
just brought them to and then you're being kind of
I know started.
oh, so first
Exactly.
oh, there's this guy out there.
I live in class there, in our still.
Very cool.
Yeah.
Okay, that makes perfect sense.
Correct. Yeah. So I think I'm going to use our
That's like big ones.
I
got you.
I think it's like 75.
This is cool. Living in Georgia?
Yeah, I think we'll find out, but I think I'm looking forward.
Someone is trying to hire us.
Okay.
If we sell our house, we can go.
Okay,
I think it's like at least that's. One of my very good friends was for years, Eric Brown. He's actually Emilio's. Oh, really? Yeah. So you were Marvin was a
yeah, so Marshall was Emilio.
So Marvin, Emilio.
Okay.
So he's my father.
Yeah, I mean.
Each other, yeah. Would be good.
We're waiting for.
I think we're waiting to start and yeah.
Well, going to starting. You guys is
So.
Yeah, there's no problem. Yeah.
Alex, you can sit down. Thank you. I think we can start.
Okay. Yeah, should we just minimize this thing?
Okay, hi everyone. It's wonderful to see you again at eMERGE. I'm Yi, PhD candidate in Systems Engineering at Berkeley, and I'm the organizer of eMERGE. The weekly eMERGE seminar is a dedicated platform for early career researchers who are pursuing academic careers to present research, refine ideas, and build a community among peers working at the intersection of mobility, energy, infrastructure, and sustainability. Today, we are very excited to welcome our sixth eMERGE speaker, who is Devansh Jalota, who is currently a postdoctoral researcher at Columbia University and will join the faculty at Georgia Tech the coming fall semester. We are happy to host Devansh not only for his academic excellency, but also super proud of his Berkeley roots. Devansh was an undergrad here at Berkeley CEE, studying in this Davis School where we are now, and working with several Berkeley professors, including Professor Bayer, and before he went to Stanford for his PhD. Devansh's research develops data-driven learning algorithms and incentive schemes to advance both the science and practice of market design for sustainable and socially aware resource allocation, with applications in future mobility systems and electricity markets. So today he will talk about algorithmic sustainability for resource allocation in large-scale social-technical systems. And without further delay, please join me in welcoming Devansh.
Great, thank you so much. Perfect. Great. Thank you so much, Yi and Scott, for this great invitation. It's great to always be back at Berkeley. So yeah, I guess without further ado, let me start by talking about the topic on algorithmic sustainability for resource allocation, particularly focusing on large-scale sociotechnical systems, which is really what a lot of my research during my PhD was really focused on. So just to set some context, we very much live in a resource-constrained world, be it the limited access to energy resources, the limited availability of road space, which often leads to quite poor traffic congestion outcomes, or even the limited availability of vaccines during the pandemic. While these applications are quite diverse, they all raise the same fundamental economic question, which is how do we best allocate our available set of scarce economic resources amongst the population, potentially when we have strategic agents that are trying to optimize their individual objectives or utilities within the system. And the age-old economic answer to this question has been the design of so-called market mechanisms, wherein we seek to set the right rules of the marketplace. For instance, we are designing some form of a pricing-like mechanism to ensure that the right resources go to the right groups of people while we align agents and incentives in the process of doing so. And indeed, market mechanisms have made their ways into various aspects of our everyday lives across a range of applications, in particular for the three I highlighted on the previous slide, where electricity markets are used to allocate energy resources. Congestion pricing, as we've recently seen with New York City, is used as a mechanism to improve traffic congestion outcomes. And of course, a wide range of vaccine allocation mechanisms were also adopted during the pandemic. And moreover, modern day advances in computing and the proliferation of data have only opened up many more new avenues for designing these market mechanisms, from online advertising to a range of different marketplace platforms such as Uber, Lyft, and Amazon, and more recently, even in a range of smart mobility contexts. Now, while there's been a proliferation of data, it has also introduced many new challenges in the design of market mechanisms in practice. So, for instance, market mechanisms that are often geared towards efficiency maximization outcomes often end up raising quite serious fairness or equity concerns. And a case in point of this was actually congestion pricing for traffic congestion mitigation, which was not deployed in New York City until very recently, with one of the main issues being cited as the resulting fairness and equity impacts on lower income users. Another issue with regards to the proliferation of data is that data is often plagued with potential uncertainty and moreover can raise quite serious privacy concerns that often render existing mechanisms that rely on having access to complete information on user attributes or preferences as often completely inadequate for a range of decision-making contexts. And finally, the abundance of data also raises concerns with regards to the easy or strategic manipulation or gaming of information, which also leads to a potentially new set of security challenges. So consequently, what we really have here is that our traditional worldview of designing market mechanisms typically focused on these efficiency maximization objectives, but we really need to incorporate these different societal considerations such as fairness, privacy, and security in the design of market mechanisms for modern day resource allocation challenges. However, incorporating these different societal considerations often raises new and interesting technical challenges. So for instance, fairness and security concerns often introduce new constraints over the allocation of resources, under which computing the optimal resource allocation strategies or the resulting equilibrium outcomes often becomes computationally impractical. Moreover, when it comes to privacy and uncertainty, oftentimes existing market mechanisms rely on having access to complete information on user preferences or attributes. However, we might not really have access to that information in practice because of privacy and uncertainty concerns. So consequently, what we really need are new tools and methodologies to be able to address a variety of these technical challenges that tend to arise when we incorporate these societal considerations in the design of our market mechanisms. And this really brings me to the core focus of my research, which is to leverage tools from operations research, computer science, and economics to be able to advance both the science and practice of market design for socially sustainable resource allocation, particularly emphasizing on sociotechnical systems. So in particular, within my research, I seek to consider a variety of different aspects of societal sustainability, not just looking at efficiency, but also these other societal factors that I highlighted in the previous slide. And in particular, in my work, I focus on two predominant research thrusts. The first is more on the foundational or methodological front, wherein I seek to take a variety of these societal factors into classical resource allocation models and develop new tools and algorithms, in particular to address the various of the technical challenges I raised on the previous slide. Through my work, we've developed both optimization-focused approaches, as well as data-driven and online learning algorithms through the work to address a variety of these technical challenges. But really the core unifying feature across my research is to use tools from game theory and market design, which is necessary to capture the different incentive structures of the different stakeholders typically involved in these various resource allocation settings. So that's more on the methodological and foundational front. But a key other aspect of my work is to really also pursue application-driven research, wherein I seek to take these theoretical advancements to important societal applications, which have in effect also influenced my methodological work as well. On the applied side, a key focus of my work is on future mobility systems, And I also have some work in other areas, including electricity markets and a range of settings where artificial currencies are increasingly being incorporated into our daily lives. So with that overview of my work, the focus of today's talk will be on the first two aspects of social sustainability, particularly on fairness and security. And in particular, we're going to be focused on addressing some of the computational intractabilities that tend to arise when we incorporate these different constraints with regards to fairness and security in the design of our resource allocation mechanisms. And in particular, I'm going to highlight to you two key vignettes from my research agenda, particularly focused on developing approximation algorithms to these computationally challenging or NP-hard problems that often tend to arise when we incorporate these fairness and security considerations, and I'll emphasize their applications within smart mobility or transportation contexts. The first vignette I'm going to focus on will be on fairness issues in congestion pricing. So of course, that's become a topic that's hotly debated nowadays, particularly given its recent deployment in New York City. And the second topic I'll focus on will be on security gains, where we actually had this application on parking enforcement at Stanford, where we got data from the Department of Public Safety, and we were actually able to test the efficacy of our algorithms on some of the data sets that they provided to us. In both of these contexts that I'm going to highlight, the source of the hardness is really going to arise from the nature of the constraints that we have in the problem. And in both settings, we're going to develop certain relaxations of the originally NP-hard problems that are not only computationally tractable, but also achieve good performance guarantees to the original problems we were looking to solve. Okay. So with that, here's the agenda for the rest of this presentation. So I'll just start by going into the two projects that I highlighted on fairness and congestion pricing and on security gains. And then finally, if I have some time, I'll briefly talk about some directions moving forward. And of course, if you'd like to find about some of those, you can do that at my website here. Okay, so let's start with the first topic on fairness and congestion pricing. And again, please feel free to interrupt if you have questions at any point. So with that, I'll just start by briefly introducing, going through the model, our approach, and then finally I'll. So of course, I don't need to motivate the audience here that traffic congestion is of course a massive problem today. And one of the main solutions that we as a society have developed to the issue of traffic congestion has been that of congestion pricing, where the key idea is that we toll certain roads or regions of our transportation network so as to improve traffic congestion outcomes within those roads or regions. However, if we actually look at congestion pricing in practice, we realize that its real-world deployment has largely been quite limited and quite politically charged, in fact. And one of the major reasons for this is its associated fairness equity concerns, wherein congestion fees are often described as imposing a tax on the working class. And given its regressive nature, it is met with a large amount of public opposition, and in effect, its limited adoption in much of the world. And one of the main reasons for the limited adoption of congestion pricing has really been this tension between the possible efficiency gains of congestion pricing in terms of improved congestion outcomes and its potential negative fairness or equity implications on certain groups of the population. Yes.
Not that I doubt the regressive nature, but do you mind explaining a little bit the explanation of how it's regressive? I wanna really understand that.
Absolutely. So the key thing about when we think about regressive taxation, for instance, right? It's about, are we charging lower income people a larger proportion of their income to, let's say, use the same roads as compared to the higher income, right? So that's kind of where things become regressive. And I guess like the way it plays out in the transportation context is really that now these lower income users, as I'll highlight in this next example to highlight this trade-off between the efficiency and equity, is essentially that now lower income users will be using much longer roads to make the same trips that they would otherwise have probably made on the same roads that maybe the more wealthy sections of society may have made. All right, so somehow the regressive impacts are like, if you think of it in the congestion pricing context, if I'm using the same road, I'm using more of my income if I'm a lower income user to use those roads, but also maybe it's having these travel time impacts as well on these lower income users, where they're probably having to use much longer roads to get to their destinations. Great, and hopefully this example will try to highlight that a little. So let's consider this very simple and stylized example to highlight this trade-off of a traffic routing problem. Let's say that we wanted to route 5 units of travel demand between San Jose and San Francisco. And just for the stylized nature of this, let's say that the travel time on the blue route is a function of its flow given by 2x1 squared, and the travel time on the other green route is just a fixed constant of 50. Okay. Now, in this case, if we do not do any form of polling or congestion pricing in the system, well, users will just simply selfishly minimize their individual travel times within the network. And the resulting outcome will be what we call a user equilibrium, where in this case, all the 5 users will end up using the blue route, right? And note that such an outcome is a user equilibrium because no individual user could have improved their travel time by shifting from the blue route to the green route within the system, as they're incurring a travel time of 50, and if they shifted to the green route, they would not improve their travel. Okay. However, clearly, as you may have already noted, by putting all the 5 users on the blue route, we've really overly congested the system, resulting in a very high total system travel time, in this case of 250, as with 5 users, each incurring a travel time of 50 within the system. So in effect, the outcome is potentially quite inefficient. So in order to mitigate some of these inefficiencies of user equilibrium routing, this is really where congestion pricing has a possible role to play, wherein if we set the right poles within the transportation network, for instance, in this case on the blue route, we can possibly get a better distribution of passengers within the system to steer ourselves to a system optimum, where we, for instance, minimize the overall travel time of all users in the system. So in particular, you could imagine if I set the right poles on the blue route, I could get a better distribution of passengers within the system, where now only 3 are using the blue route to the green route, and we can significantly improve the travel time in the system from 250 down to just 154 within this case. Okay. So, well, using the right congestion pricing strategies can possibly improve our efficiency of the system. But if you actually look at the outcome more carefully, what you realize is that this can have quite serious fairness or equity implications. So in particular, if we look at this outcome, now we have 3 users using the blue route, incurring a travel time of just 18, but 2 users using the green route, incurring a much higher travel time, almost 3 times the travel time of 50, just to make the same curve. And this would typically be the lower income users who then end up having to bear the brunt of these much longer travel times within the network. This really gets to, I guess, maybe to some extent Scott's question about the regressive nature of this, and that we're really putting the burden of these longer travel times within the system potentially on certain groups of the population more so than others. Okay. So overall, what I've highlighted here is this efficiency fairness trade-off when it comes to traffic routing. So the user equilibrium setting is fair in that if we look at the travel times of any 2 users between the same origin and same destination, they have exactly the same travel time. So in that sense, it's fair, but it's potentially quite inefficient with very high travel times. At the other extreme, we have the system optimum, which is by definition efficient because we're optimizing the efficiency of the system or minimizing travel times, but it's potentially quite unfair. In this case, if we look at the ratio of the travel times of users using the same origin and destination, it's actually almost on the order of, right? So this really brings me to the key contributions of this part of this talk, where we essentially try to resolve this trade-off between the efficiency and fairness via a 2-step procedure. The first part that I'm going to present to you is this computationally efficient traffic routing algorithm that effectively trades off these objectives of efficiency and fairness. And we do this via developing a novel convex program called ITAP that I will introduce. And then we'll combine this routing algorithm that we develop with a fair congestion pricing scheme. In fact, providing the first set of congestion pricing schemes for fair routing in the context of general road networks. And together, by combining this algorithm with this congestion pricing scheme we developed, we're able to effectively balance these 2 different objectives of efficiency and fairness in traffic routing. Okay. Let me now just more concretely define the model and the setup that we have. So first, let me start by just formally defining the 2 metrics of performance we're going to use, that of fairness and efficiency, that we'll be interested in. Okay, so first, how are we going to measure efficiency? The way we'll measure efficiency is via a quantity called the inefficiency ratio rho, which is just the ratio between the total travel time of a traffic assignment X divided by the best achievable total travel time in the system, which is that of the system optimum solution, right? So note that this quantity can never be less than 1. Right? Because in the denominator, we have the minimum achievable travel time within the network. So that's efficiency. What about the other metric? We're also interested in optimizing some notion of fairness. And the way we'll think about fairness is via a quantity called the unfairness, which we'll define with this via this function u, which will take in a vector of path flows within our network, and it will compute the maximum across all origin destinations, the maximum ratio of the travel times of any two given users that are traveling between that origin and destination. Right. So this is just generalizing the fairness notion I presented earlier for the single origin destination example, just to a multi-origin destination case where there are many possible paths within the network by just taking the maximum across those origin destination pairs of the maximum ratio of the travel times of any two users that are using that origin destination.
A question.
Yes.
So I understand SO stand for social optimum.
System optimum.
A system of
Yeah.
optimum. Yeah, and I understand why X and has such a upscript. Can you explain why F, the function F, also have such a upscript?
Oh, I see. So this is just a function for the system optimum.
Okay.
That's kind of it. Like I think on this slide, I'm going to define what this FSO exactly is.
Yeah,
But it's basically just the total travel time.
but it doesn't have any like optimal. What's the optimal? Here?
Oh, it's just this is just how I'm defining this.
I see. I see.
There's nothing more to it.
I see.
Yeah. Great. So, okay, so we've defined these two different notions of fairness and efficiency that we're interested in. But how do we balance between these two different objectives? And we're going to strike a balance between these two different objectives. We are studying a classical problem called the beta unfair system optimum. Okay, let me just present what this problem is. So in the objective, we're going to minimize over the set of all feasible traffic assignments within the system, the total travel time within the network. So that's our efficiency maximization objective that we're going to be interested in. But we're going to do this while satisfying certain unfairness constraints, essentially saying that our total level of unfairness must be no more than some parameter beta, which you can think of as being specified by some transportation detail. Okay. So just to be very clear, what this unfairness constraint is saying is that no user's travel time can be more than beta times the travel time of any other user that is traveling between the same origin and destination. Okay, so essentially, just at a high level, we're solving an efficiency maximization or a travel time minimization problem while satisfying fairness constraints. Okay, it turns out that solving this problem is NP hard. And one way to see this is the fact that our unfairness constraints are actually non-convex. Yes.
Just out of quick curiosity, are there different metrics of fairness in which it's not NP hard?
That's a fantastic question. So absolutely, one can define other notions of fairness where you would not have this kind of computational challenge. Though this is kind of like been one of the most widely accepted definitions. Of course, not to say like you can't do different kind of definitions. So within the paper, we study a range of different definitions. I'm just using this for the purpose of presenting the work. But yeah, you could like, I don't need to take a maximum across all origin destination pairs. I could take some other aggregation function. I could take the Gini coefficient of the travel times. I could do all kinds of things to define fairness. And I guess a lot of these other ones have also been used, but this is kind of the most predominant notion used in the literature. So I'm really using that for just, I guess, pinning down this one. Great. Okay.
Actually, is there an
Yes.
algebraic formal relation that can be driven between fairness and regret? I mean, regret has a very different definition because
Correct.
it's min-max.
Yeah.
But obviously the relation, the more unfair, the more regret. But is there any formal relation that can be useful to us?
Interesting. So you're saying some kind of an equivalence between regret and
I think things in regret also materialize themselves as NPR, so
I
you
see.
don't gain much, but I'm just curious.
Yeah, I see. Yeah, I guess I've not really thought much about it, but I think when I present my algorithm to you, it might make, because so the algorithm that we develop is not like, it's kind of agnostic to the kind of unfairness measure that you have, right? So you can use that algorithm no matter kind of what, and maybe that kind of may get to what Alex is asking. So, okay, let me just briefly talk about some
I have a quick question. For a desirable value of data, in case of indivisibility, how do you deal with that?
in case of indivisibility.
Infeasibility.
Oh, infeasible. Okay, so as long as beta is at least one, which is, I guess, unfairness of one is the minimum possible, right? In the definition that we had. But the bottom line is that the beta of equal to one is guaranteed to be achieved because the user equilibrium is always gets you a beta of 1. So you'll not have a problem with it either. Yeah. Oh, great. Perfect. So just a quick note in related literature. So there have been a lot of attempts to solve this beta unfair system optimum in a variety of different ways. But one of the issues with existing approaches is that they're often very computationally prohibitive, often relying on solving large-scale mixed integer programs. Another issue is that they often lack theoretical guarantees in terms of how good the resulting solution is to the original problem we're actually looking to solve in terms of efficiency and fairness. And moreover, while they develop some algorithm to solve this beta unfair system optimum, they often don't accompany with a pricing mechanism to actually implement that outcome as flows in practice. And in this work, we're going to overcome each of these three issues by not only developing a computationally efficient algorithm, but combining that with robust theoretical guarantees, and moreover, developing a pricing mechanism which immediately follows from the convex programming approach that we developed to actually implement those routes as flows in practice. Okay. So let me go through our approach. So the way our approach works is as follows. We're just going to essentially develop a novel convex program called the interpolated traffic assignment, which is going to interpolate between the system optimum and the user equilibrium. Okay. So just to be clear, we have the system optimum traffic assignment for more general road networks. We're just trying to minimize travel time, the total travel time in the system. We saw earlier that this problem is by definition efficient, but it may lead to unfair outcomes, as we saw with that example that I said. Okay. At the other extreme, we have the user equilibrium traffic assignment problem given by the solution of this particular convex program that we have here. And the key property of this particular convex program is that all users between a given origin and destination incur exactly the same travel time. And this kind of gets to the question we had earlier about the feasibility with regards to beta, that a beta equal to 1 is always possible because we can just solve this particular problem. Okay. Now, the solution of this problem is by definition going to be fair. We'll have an unfairness of 1. But it may possibly be inefficient, again, as we saw with the example earlier. Okay. So what our approach is essentially what we call the interpolated traffic assignment, where we take a convex combination between the user equilibrium and system optimum objectives. Okay. And the idea behind doing so is that we want to achieve the best of both worlds, try to get the efficiency gains of the system optimum and the fairness gains of the user equilibrium.
In scenario 2, would you say that the unfairness is, I mean, obviously, for simple E, regardless of the routing, every is equal fairness by definition of Nash.
Yeah.
But it doesn't say that the level of fairness for different ODs, right? Because you could be completely screwed by that.
Yeah, absolutely. So yeah, we're not looking at different ODs.
Yeah.
In the paper, we have some discussion about what to, but I have no way to define. People have thoughts on that. Yeah, that's exactly. Yes, that's great. Okay. So let's just summarize what we've done. We started with this original data unfair system optimum, which is an NVR problem, like I mentioned earlier. And instead, what we're going to do, and what we've done here is we're just going to approximate it via this ITAP problem, where we've removed these non-convex unfairness constraints and instead replaced our objective with one that just interpolates or takes a convex combination between the user equilibrium and system optimum objectives.
I'm sorry to keep noting on the left one, if you remove the constraint, it's convex, right?
If you remove the constraint, it's convex. Then you're just optimizing then the two objectives would become the same for alpha equals 1.
So the real complexity comes from the constraint because of the definition.
Because of the definition, exactly. Yes, absolutely. Yeah, and I think it's been shown for a range of different definitions of unfairness that it's NP-hard. I've only presented to you one such definition, but yeah. Okay. So yeah, so we've done this approximation, but a question that you might be thinking is, well, how good is this approximation to the original problem we're actually looking to solve? And I'll answer this question to you both theoretically and numerically in the next few slides. Let me first just briefly present the theoretical bounds. So essentially out here, we can just look at how good does our algorithm do theoretically in terms of the inefficiency ratio for any given convex combination parameter alpha that we choose between 0 and 1. And this is just a plot that kind of plots this more general bound that I have here for a very specific transportation network on this, on the left hand of this particular slide. Okay. Similarly, we can also get certain bounds on unfairness for our ITAP procedure that we have here. So let's suppose that I want an unfairness of beta equals 3 within my system. Then essentially, if I choose a convex combination parameter anywhere between 0 and 0.5, I'm guaranteed to get an unfairness of 3 within my network. Okay. So these are just some bounds that apply for general transportation networks or general multi-commodity flows that we can have within the system for both efficiency as well as fairness. But it turns out that if we actually restrict ourselves to some specific classes of transportation networks, in particular, the classical Pigou style network, where we have a single origin, single destination, and two links connecting the origin to destination, we can actually show that our ICAP procedure will give us the optimal solution to the original beta unfair system optimum. So that is, we can actually optimally solve the original NP-hard problem via the ICAP procedure that we have developed. Oh, so that's everything on the theoretical front that I wanted to present on this particular part. But how well does it do when we actually test out our algorithm in practice compared to a state of the art? So here I'm presenting some results with regards to the runtime of our algorithm compared to a state of the art approach. And you can see that our algorithm actually improves upon the runtime by several orders of magnitude compared to the state of the art approach. And the real reason why we get such strong computational savings across a range of different transportation networks that we test against really stems from the following key fact, that if we take our ICAP objective that we have here, by the fundamental theorem of calculus, we can actually just write it as a user equilibrium traffic assignment objective with a modified travel time function. And so the bottom line is that because we have very efficient algorithms to solve this user equilibrium problem, we can now just port those over to be able to very efficiently solve our system of our ICAP problem also very much.
So there's Frank.
Oh yeah, so yeah, for instance, you can just use Frank Wolf.
Like on column for that. Yes.
Sorry, this column?
Yeah, so that's.
Oh yeah, so we are using Frank Wolf within our exact. Great. So this is on a computational viewpoint that we're able to do well compared to the state of the art. But what about actually if we compare the performance of our algorithm on both metrics of efficiency and fairness? So out here I'm plotting the Pareto frontiers of the inefficiency ratio to the level of unfairness of our algorithm compared to the state of the art on a variety of different transportation networks. And what you can clearly see here from these plots is that if you look at any desirable level of unfairness, particularly lower levels of unfairness, which is where we would likely want to operate in practice, then our algorithm actually achieves lower total travel times or better efficiency compared to that of the state of the art for all of these six transportation networks. And in fact, if we just restrict ourselves to the top three transportation networks, pretty much for any level of unfairness that we want, we're able to do better compared to the prior algorithm.
Can you say just a few words about this state-of-the-art benchmark? What is the idea?
So yeah, so the basic thing is that they're formulating. So essentially, they're taking the beta unfair system optimum and they're solving a sequence of these constrained shortest path.
Okay.
So basically, we're adding these unfairness constraints. So they're actually like they're solving the same system optimum problem, but now with these additional constraints. So actually, they're solving the sequence of NP-hard problems. But that's kind of their best estimate that they had developed for the network. And so, which is why also you get these kind of massive computational savings of our approach compared to that. And I guess it also turns out that we get a much better performance compared to that particular application. Okay, great. So let's just summarize what we've seen so far. So we developed this computationally tractable convex programming relaxation to the beta unfair system optimum. Yeah, we saw that it was computationally efficient. We can also get certain bounds in terms of analyzing its efficacy on both efficiency and fairness. And moreover, we can get some nice numerical guarantees as well compared to a state-of-the-art algorithm.
But back to the question have been asked several times on the notion of unfairness.
Yeah.
You prove for this notion you selected. How about other notions?
Absolutely. So the thing is that for some notions, I guess you can't really say anything, but then you can also say that this particular notion of unfairness that we used upper bounds a range of other notions.
Okay.
So for any of those notions, you can translate the same guarantees. But yeah, I guess for some other notions of unfairness, kind of
I see.
cannot get anything theoretically, or I guess at least we didn't spend that much effort in kind of getting theoretical bounds for all of those.
I see a question from Rating. So from on Zoom. So Rating, if it's a question, feel free.
Yeah, can you hear me?
Yeah, we can hear you.
Thank you, thank you. I have a question about the original problem where we have only one constraint that's UG less or equal to beta. I'm thinking that if for a more complex system, there will probably be other constraints as well, like physical constraint of the system. And in that case, if we set a beta is it possible the problem just becomes infeasible because we want to reach a certain level of fairness? And how do we decide the beta in those scenarios? That's my question.
Yeah,
Thank
so
you.
I think this is a question that was asked on within the room as well about the feasibility when you choose different values of beta. So it actually turns out that for any beta that is larger than 1, this problem is always guaranteed to be feasible. And the reason for this is that the user equilibrium traffic assignment problem guarantees that we achieve a beta of equal to 1.
I think there's another part of the question that maybe deserves
Okay.
clarification is that besides the unfairness and equality constraint, there are all the remaining travel
Absolutely.
assignment
So
problems that have been- you just suppress that.
that's all suppressed in this script X that I have here. I've just avoided all that notation just to keep life
Focus.
simple and to focus on what's the new element of this problem relative to classical ones. But you'll have all the origin, destination, demand constraints, flow balance constraints, non-negativity constraints, all of that embedded within that script X that we have there. So this is a completely general multi-commodity flow problem that we are kind of solving. Yeah.
Thank you, Ricky.
Okay, perfect. Great. So yeah, I guess we have all these benefits of ITAP in terms of being able to solve this original problem that we started with, but it still leaves open the following key question that can we actually implement this outcome in practice? For instance, we are designing some form of a congestion pricing mechanism to ensure that we can get these fairness constrained flows actually as equilibrium. Okay, so that's the next part. So to talk about this, I'm going to first need to define how do users behave within our system. So we're going to assume that users are just going to minimize the sum of their travel time and tolls. And in particular, that users minimize their value of time multiplied by their travel time plus their tolls. This is kind of the most classical way you can think about what users would do within the system. And for the purposes of this talk, I'm going to assume we have homogeneous users. So everybody has the same value of time, and I'll normalize the value of time to 1. So users are just minimizing the sum of their travel time plus their tolls. Okay. So let's see how we can derive a pricing scheme from ITAP. Well, we started with this particular interpolated traffic assignment objective that we had. By the fundamental theorem of calculus, we can rewrite it as a user equilibrium traffic assignment objective with a modified travel time function as a shorter. Okay. Now, it turns out if we look at the optimality or KPT conditions of this problem, that we get the following fact. If there is a positive flow on any given path, then for a given origin destination, the following quantity must be minimum, which is basically the sum of the travel times plus some additional delta term. Okay. We now compare the two sides of this slide. What we realize is that if we set the toll equal to this additional delta term, then those are exactly the prices that we would want to set to achieve an equilibrium outcome within the system. And this particular toll that we set are what we call interpolated marginal cost tolls, because it's the traditional marginal cost tolling term multiplied by some interpolation or convex combination parameter I. Okay, so that's the pricing mechanism you would get with homogeneous users. You can also generalize that to the setting where we have different values of time, heterogeneous values of time across users. And for that, we develop a linear programming approach, but I won't go into the details of that in the interest of time. Okay, great. So let me just very quickly conclude. So in this part of the talk, I talked about a new computationally efficient algorithm called ITAP to effectively balance these objectives of efficiency and fairness in traffic routing. It has a variety of benefits that I demonstrated, and also it yields a very natural class of congestion pricing mechanisms to actually implement the outcome of ITAP in practice. And moreover, we can also, as some of the questions have already alluded to, we can extend to a variety of different notions of unfairness, in many cases numerically, but in some cases theoretically, this one. Okay. So just to, I guess, wrap up on this part of the talk, what I'll mention is that this work on developing this convex programming relaxation of this originally NP-hard problem is, of course, just part of a much broader agenda on studying equitable congestion pricing, which is actually a topic which I've worked on throughout my PhD in a variety of different respects. So in particular, in another project, we think of congestion pricing not just from the lens of tolling, but also from the lens of can we use these collected toll revenues potentially to give refunds to the right groups of users in the population to achieve better equity outcomes. And in the game theoretic frameworks that we study, we show that if we design these refunding schemes appropriately, we can actually provably improve system efficiency without worsening the level of wealth inequality within the system. And moreover, in some more recent work, we've been studying some recent deployments of equitable congestion pricing schemes in the Bay Area, namely credit and discount-based congestion pricing, which are essentially designed to provide subsidies to low-income users to be able to access toll roads or express lanes on highways. Okay. So with that, I guess I've concluded the first part, but maybe I can just pause here in case there are any questions. Yes.
Can you go back one slide, please? Can you explain a bit how this revenue funding refunding? Works?
Yeah, so the basic idea is that like once you collect the revenues from the different user, so I guess so it works in a two-stage way, right? So you're setting tolls on the different roads, you collect the revenues from these tolls, and then you can give some or all of the revenues back potentially as cash payments to the different groups of users in the population. And out there, we're optimizing, we don't have fairness constraints anymore. We're literally trying to optimize for two metrics. One is efficiency. So you can think of a similar notion to what we presented. And the other is just the Gini coefficient in terms of the wealth inequality within the system, right? So we're trying to optimize for both wealth inequality and system efficiency simultaneously, and trying to develop what we call CPRR schemes, congestion pricing and revenue refunding schemes that try to achieve both simultaneously. But I'm happy to go into more details on that.
Please move on.
Okay.
And that will be best if we can.
Sounds good. Okay, great. So yeah, let me just very quickly move to the second part on security games, continuing our work on trying to develop these approximation algorithms for some of these computationally challenging problems. So let me just quickly introduce the setup. Or just introduce the problem. So of course, fraud is very much ubiquitous in a range of applications, but also can possibly lead to quite detrimental outcomes, right? So environmental non-compliance is a key example where a water treatment facility may possibly have an incentive to save on the cost of complying with water quality regulations, but can possibly put the lives of residents at risk. Another example that we face almost on a daily basis, which is that of traffic or parking violations, which is that we as creators often face a decision, should I purchase a parking permit today or not? Or maybe should I engage in overspeeding? However, doing so can possibly lead to poor outcomes on roads with regards to traffic jam or road safety. While the examples of where fraud can occur in practice can be quite distinct, users are typically engaging in such practices potentially to strategically obtain some benefit that they would otherwise not have been able to obtain had they just operated within the bounds of lawful harm. And it is this exact strategic interaction that we're going to try to capture within this framework. Okay. So essentially, what we're going to do is we're going to formulate this problem of policing fraud as a resource allocation problem, where we have a police authority with access to a certain set of police officers or security resources. And we have these possibly susceptible nodes or locations in the system. Think of these as the different water treatment facilities across California. And then the question that we want to ask is, how do we best allocate our limited set of resources across these different potentially susceptible nodes or locations to achieve some potentially desirable outcome where now, let's say, more water treatment facilities are complying with these regulations. Analogously, you could think of the same problem in the parking enforcement context, which is how do we best allocate our police resources to the different parking lots on, let's say, Stanford University's campus to ensure that now more commuters are purchasing parking permits. Okay. So in order to study this particular question that I just highlighted, we're going to model this problem as a security game that is played between an administrator and users. And out here, the administrator has a certain budget of security resources that it has access to and can possibly levy fines on users that are found engaging in fraud. Okay. So for this problem, I'm first going to present to you just some basic ideas with regards to how we can actually analyze this problem theoretically by presenting you to the resulting equilibria and the optimal strategies of the administrator within this game under several information assumptions and under two different administrator objectives that are revenue and payoff maximization. And I'll be clear what I mean with these terms in a few slides. Let me just preview the nature of the results we'll get. It'll turn out that computing the optimal resource allocation strategies or the equilibria for security game end up being NP hard. However, because of the hardness of these problems, we can then develop certain approximation algorithms for which we get certain approximation ratios, as well as some resource augmentation style guarantees that I will present to you. Okay. that's everything I'll present on the theory front. I'll also then present some numerical experiments where we actually got real data from Stanford's Department of Public Safety, where we were able to test some of our algorithms on their data sets. And then we also have a variety of extensions to our framework that we studied in the paper, which I won't go into here in the interest of time. A very quick note on literature. What I'll just mention here is that our work is really the first to provide algorithms for which we have provable guarantees. So there's a very general class of security games called multi-resource Bayesian stack overflow security games. Here, the Bayesian refers to the fact that the adversaries or users in our system can have many possible types. So not just a single type, but many possible types. And the multi-resource refers to the fact that the administrator can possibly have a budget of security resources rather than just a single resource that they need. So it's indeed a very general class of security games that we study. Okay. So let me just briefly present the model. So we have an administrator with these R security resources. Think of these as the enforcement or police officers. And we have these L locations that are susceptible to fraud. Think of these as the different parking lots on Stanford or Berkeley campus. Okay. Now, each location L is going to be characterized by some type theta, which is going to be given by a triple. So lambda refers to the number of users of that given type. D represents the benefit that a user of type I would obtain when they engage in fraud at location L. Think of this as the savings you get from not purchasing a parking permit on a given day. And P represents the payoff that the administrator receives from preventing fraud at a given location. So you can just think of this as the earnings you get from parking permit purchases at a given location from given type of users on a given day.
It's the payoff from reducing fraud or the payoff from punishing fraud?
This is the payoff from reducing fraud. So the payoff from punishing fraud would be the fines I would collect.
Yeah.
Right. So I'm going to go to those two objectives in just a bit as to what the administrator is optimizing for. But this is the payoff from reducing fraud.
Okay.
You could also get payoffs from, and so that's why we study these two objectives: one of revenue maximization and one of payoff maximization.
Got it.
So you could think of this as how much fraud I've reduced.
Yeah.
And you could think of the revenues as just how much fines I've collected from this. Exactly. That's a great question. Okay. And as noted, the administrator, as you would have in a parking enforcement context, can possibly levy a fine of K on users if they're found engaging. So let me just quickly talk about the strategy spaces of the two different groups of users within the population. So the administrator essentially will select some mixed strategy vector sigma to allocate its available budget of security resources, where sigma L just denotes the probability of allocating a resource to a given location, where the sum of the sigmas must be no more than our overall budget of. Okay. That's what the administrator does. What does the user do? The user essentially just decides, should I engage or not engage in fraud at a given location, given the administrator's strategy sigma. So in particular, we'll let YLI of sigma denote the probability that a user of type I at location L engages in fraud, given that the administrator plays strategy sigma. Okay. So these are the strategy spaces of the two different users. And we're going to now study this problem under two different administrator objectives as highlighted under revenue and payoff maximization. Okay. So let me first start by talking about the revenue maximization problem. So what we're going to be interested in here is essentially solving a bi-level program, where in the upper level, the administrator maximizes its overall revenue from the fines that it collects from all users within the population, while in the lower level, users are going to just best respond by deciding whether or not to engage in fraud, depending on whether the gains outweigh the losses from fraud. Okay, so that's the revenue maximization problem. Analogously, we can formulate a payoff maximization problem, where instead of maximizing the revenues from fine collections, I'll maximize the overall payoffs that I can achieve within the system with a similar bi-level structure that, to that we have in the revenue maximization set. And of course, both of these problems have relevance depending on the context that we are interested in. And I'd be happy to talk more about the practical sort of implications of these objectives offline in the interest of time. Okay, so what's our goal? Our goal is to characterize what the optimal or the near optimal solutions to these bi-level programs looks like, which is essentially to characterize what the equilibrium outcomes in our case really take shape. Let me just present to you some of the key results that we have here on the theoretical front. And essentially our results can be summarized in this 2x2 grid for the two different objectives and the two different type assumptions that we have. The first assumption that we have is of homogeneous user types, where user types can differ across locations, but at a given location, all users have exactly the same type. So that's the homogeneous setting. And then we have a heterogeneous setting where user types essentially can differ at a given location as well, just generalizing the homogeneous case. Okay. So let's see what our results are. So let's look first at homogeneous revenue maximization. So it turns out that homogeneous revenue maximization is actually easy in that we can develop a polynomial time algorithm to actually compute the optimal strategy of the administrator in that setting. However, it turns out that homogeneous payoff maximization is computationally challenging or NP hard, but we can develop certain approximation algorithms. In fact, a greedy-like algorithm that can get us a half approximation or half of the optimal payoff as that of the optimal payoff maximizing outcome that we can achieve. And in fact, we can also actually obtain a stronger result by developing a resource augmentation style guarantee, which states that if we augment our greedy algorithm with just one additional resource, you'd get at least the payoff as that of the optimal strategy without that additional resource, right? So essentially, it's often better to just hire one more police officer than to, I guess, invest a lot of computational effort in trying to solve this complex optimization problem that we have. Okay. So that's all the results on the homogeneous for the homogeneous setting. Let's look at what happened in the heterogeneous setting, which is of course the more general interesting setting. So it turns out that heterogeneous revenue maximization is no longer easy in that it ends up being NP hard, but we can develop similar approximation style guarantees in the heterogeneous revenue maximization setting as well. And in fact, all of these results actually very naturally port over to the heterogeneous payoff maximization setting as well that we have. Okay. So in the interest of time, I'm just going to spend just the next 2 or 3 slides just highlighting to you some of the key ideas that we have for the heterogeneous revenue maximization setting, just to build some intuition on the results that we have. Okay. So it turns out that solving this problem ends up being NP hard. So the heterogeneous revenue maximization problem is NP hard. And just to see this, I'll highlight some quick geometric intuition. Okay. So in order to think about studying this bi-level program that we have of heterogeneous revenue maximization, it's first instructive to see what happens in the lower level problem. That is, how do users best respond to a revenue maximizing administrator? It turns out that the lower level problem of the user best response takes a very actually natural form, which is given by a simple threshold. So in particular, if the allocation probability of resources to a given location exceeds a threshold, I will stop engaging in fraud. If it's below a threshold, I will engage in fraud, right? That's really what you would naturally expect to happen in practice as well. Okay. So given that we have this nice threshold-like property, we can now actually plot what our revenue function looks like at a given location. So as a warm-up, let's see what it looks like for the homogeneous type setting. So just a single type of users at a given location. Well, our revenue essentially just increases linearly up to this particular threshold, after which the revenue drops to 0 because users stop engaging in fraud once we've allocated beyond a certain probability to a given location. Okay. What's nice about this revenue function is that it's continuous between the range of 0 and our threshold, and that's what enables us to derive a polynomial time algorithm for this particular set. Okay. But now let's look at what happens to our revenue function when we have heterogeneous user types or many possible types of users at a given location. Well, our revenue function no longer looks as nice, and in fact takes a much more jagged form, because now we have many different types of users, each having their own threshold probabilities at which they shift from engaging to not engaging in fraud. And so as a result, now our revenue function is no longer continuous. In fact, it's discontinuous and also non-monotone between 0 and the maximum threshold that we have here. And this is really what contributes to this problem being NP hard, which we're able to then show by a reduction from the classical partition problem. Okay, so we know that we can't solve this revenue function, we can't optimize this revenue function directly, but the question is, can we optimize some approximation of it that is potentially practical? And so essentially what we do is we optimize a very specific approximation of it, which is what we call in the paper the monotone concave upper approximation, or essentially the concave upper closure of the original revenue function. And the nice thing about this MCUA is that it can be optimized tractably, in fact, just using a greedy-like procedure that just orders the segments based on the slopes of the different segments within across all the locations that we have. And this particular procedure can be done in a very efficient. Okay, this algorithm, I'm not going to go into detail, is just doing a modified version of maximizing this MCUA of this particular revenue function. And what we can show about this particular algorithm is that it can achieve at least half of the optimal revenue as that of the revenue maximizing solution. And moreover, we can get a resource augmentation guarantee that if we augmented this algorithm with just one more resource, you'd get at least the revenue as that of the optimal solution without that additional resource, right? So again, the fact that I mentioned earlier, it's better to just hire one more police officer than to invest a lot of computational effort in solving this original NP-hard problem that we're looking to solve. Okay. So let me just conclude with some numerical experiments. So the setup that we have here is of parking enforcement at Stanford's campus. So on campus, all commuters are required to purchase certain parking permits, and they're issued citations if they're found violating the regulations. And a key aspect is that any collected citation fees go to the county, but any earnings from parking permit purchases goes to Stanford. And that's going to be a key way in which how we're going to use that to model the problem within our brain. Okay. What's the data that we got? We got 7 months of data between September 2022 to March 2023. Including all enforcement information, including the time and periods at which enforcement took place in the different parking lots on campus, as well as citation information on the number of citations that are issued across these different parking lots. Okay. And so essentially, given the setup that we have, we formulate Stanford's parking enforcement problem as a heterogeneous payoff maximization problem, as Stanford is interested in maximizing earnings from parking permit purchases. And here the payoffs just represent the earnings that we get from parking permit purchases. Let me just briefly present the results. So we tested our algorithms to the status quo and a variety of different counterfactuals for how users might behave. And what I've plotted here is just looking at the status quo presented in blue compared to our algorithm presented in orange with regards to the total revenue as the proportion of strategic users in the population changes. And what you can clearly see here is that our algorithm outweighs or outperforms the status quo enforcement mechanism in terms of parking permit earnings. But in particular, our approach has significant gains compared to the status quo, particularly as a proportion of strategic users and the population increases within the population. And that's really where the power of our security gains ratio really comes. Okay. And in particular, if you actually then pinpoint exactly the number of citations that are issued in practice within the data set that we got, we can actually show that our approach can achieve almost $300,000 of additional earnings relative to the status quo per year on that person. Okay, so yeah, I guess I'm probably already over time, so let me just conclude here that yeah, I guess we developed this model of a security game, analyzed it theoretically, presented some experiments based on data we got from Stanford's Department of Public Safety, and of course, we also have a variety of different extensions, which I'd be happy to talk about on. So yeah, I guess I'll just pause here just to say I'll probably not go into the future work part given the interest of time. But yeah, I guess that this work is part of just my broader agenda on studying. Yeah, I guess I'll just end here that. The work that I presented here is just part of a much broader agenda on studying socially sustainable resource allocation in sociotechnical systems. And I presented to you some vignettes particularly focused on fairness and security, more from the lens of approximation of algorithms. So thank you so much for listening and hope you enjoyed it.
All right, thanks, Devansh. I'll take the role as discussant. So first, just to briefly summarize, what we heard about today is really about resource allocation in different styles, right? There are two parts. The first part was trying to balance fairness and efficiency or some performance metric, which is a tremendous problem to solve for policymakers. And so it's interesting to sort of see, okay, what are metrics of fairness?
Yeah.
What is efficient? How do you define these? And you describe this, what in the end became an approximation that was like a multi-objective, convex combination and some algorithms to solve this. And then the second question, very interesting and also probably triggering in some sense with what's going on in the world, but resource allocation of security.
Yeah.
Types of resources to prevent fraud and, some similar but different themes of, how do we formulate the allocation of these resources considering the game, between some administrator and, players. Yeah, and very cool, in both cases, you had really nice motivating examples, be it, now you're in Colombia and they brought you there because they need you to solve this congestion pricing problem, right? So hopefully you're doing good there. Yeah, and then also this parking permit problem in Stanford. So with that just super brief summary, questions?
Thank you, I really enjoyed this, and I guess my question is kind of like related to, I guess, the thing that you didn't cover, which is future work. And I was just wondering, I think, going back to the fairness and congestion pricing. We're drawing some very large conclusions on that in terms of like the societal impact. And I was wondering if you considered one of your future works being, how did your fairness factor, and you said that was I think that like the commonly used one in literature. Like how well does that approximate real world fairness? Like I know that in the real world, when you're looking at like socioeconomic differences, there's a ton of geographical disparity, and different socioeconomic groups are usually like very stratified into a certain geography, and so like different origin destinations, like they might be trying to typically get to like the same type of destination from different origin. Right. And then also the effect, if you've given any thought to the effect of considering the homogeneous value of time metric, because I don't know how much that would impact the problem, but I do imagine that like, I know that some people look at tolls as they don't care at all. It's not really a monetary factor for them. They're fine paying them all the time. They just do it. And then other people will on Google Maps to avoid all toll. And I feel like that shows a very different time value.
Absolutely. Great set of questions. So, let me just go back to this particular set of slides I had while back. Just to pin. Yeah, here, right? So it's kind of like you're just getting at kind of the broader agenda on studying equity and congestion pricing, which is your question or your set of questions is kind of getting at. I of course presented you one set of notions. And I think Alex also mentioned about what happens with these multiple origins and destinations and all of that. Like, I can tell you I have tried finding the literature, I have tried generalizing the notions that we have for these multiple origin pairs. I have not come up with a satisfactory solution.
Yeah.
And I think because, it's like, how do you compare across these different origin destinations? It's just not, it's not clear how you even start by defining the problem, let alone trying to develop approaches to solve it, right? So that's more on this first topic, but then trying to go to some of the other points that you mentioned. But we do have a discussion on these other notions of fairness within that, and also where our notions of fairness break down when you look at these different origin destination notions. Because you could be very fair on our notion, but be very unfair on those different origin destinations, right? So it's kind of it's very interesting, but I guess no clear way to define it. With some of these other works, I can just like talk about that because you mentioned time value of money, right? So this work is actually entirely about time value of money in many ways, because you kind of want to prioritize users with particular time value of money compared to others.
Okay, so that's built on something that wasn't discussed in this video.
Exactly. So that's an entirely, and like the way we define efficiency there in that context is actually the time value of money weighted travel times. So here I define efficiency as the sum of the travel times, but out there you could look at the sum of the value of time weighted travel times. Alright, so it's value of time times travel time, sum that across all users. So the efficiency notion actually there is a little different. So we're kind of trying to address maybe to some extent some of the things you're mentioning. And this third set of third line of work within this area is actually interesting because what San Mateo County has recently done, as a case in point, is they've of course deployed a lot of express lanes in the Bay Area. But in particular, what they're doing now is, because of the given expansive deployments, they're giving low-income users below a certain income threshold, like 200% of the federal poverty limit, with credits or discounts that they can then use to access the express lane at a subsidized rate. So for instance, you get like, if you satisfy their eligibility criteria, you'll get some $100 or $200 of installment on your fast track, and then you can use that to use the express lane, right?
These folks have to register for that, though.
You
right?
do have to register. So yeah, there is a bit of friction in terms of registering those kinds of things. But so basically what we study within these works is what kind of equilibria arise when you design these credit or discount-based systems that they're deploying in practice. And can we design these mechanisms in better ways to achieve better equilibrium or induce better equilibrium? Right, so that's kind of aligned with how, because the bottom line is that people are actually very actively thinking about these fairness equity issues and deploying these congestion pricing systems.
Yeah, and people in the room, we can continue discussion in person later. I'll invite Rating to also ask maybe a short question, and we will conclude our seminar today. Yeah, Rating, feel free to unmute yourself. Oh. Sorry.
Thank you, Yi. I have another question for Devansh on the second part of the project. So if I'm understanding it correctly, we are dealing with a stepper game with integer decisions. And I wonder, like, first, will there be multiple equilibria? And second, do you ever observe any chance that's like jumping between multiple equilibria and cannot like converge to one? Like those situations in the problem.
Yeah, that's a great, I guess, question. So I'll tell you a little bit of what happened. So let me just, I guess this is kind of the most detailed slide in terms of trying to build some intuition. So the nice thing here is that the user's best response function, which you can see on the right-hand side, or I guess on the left-hand side of this slide, is actually a very simple best response rule, right? It's just a threshold rule. So from a user perspective, actually, it's I guess they pretty much just have a unique decision to make. The only interesting case is when you're exactly at the threshold, because when your sigma is, or the probability of allocating a resource is exactly the threshold, then you can get these multiplicity of equilibria. But the basic thing that I guess, like to break the ties, it basically depends on what the administrator's objective is, right? So the administrator is trying to maximize revenues, you break the tie one way. If the administrator is trying to optimize payoffs, you break tie another way to ensure you don't have these multiplicity of equilibria kind of issues happening. Because I guess, yeah, so that's kind of, I guess, does that answer your question to some extent, or?
Yeah.
Yeah, okay,
There's
yeah,
this, yeah.
great, yeah.
And would you mind turn to my slide again? I'm going to
yeah,
introduce our next speaker. So before we end today, next week, the fourth page, we are going to have Dr. Pei Zhao from MIT, who is a postdoctoral researcher at MIT Sensible City Lab. She will talk about heavy-duty truck electrification. The title is Feasibility of Truck Decarbonization and its Environmental and Cost Implications. She will introduce many insights she gained from large-scale data both in China and the US. So welcome if you're interested in the transportation electrification. So we will end here online, and we can continue our in-person discussion offline, and there are some great